Okay, today what we're going to do is take a little tour of what you covered in Chapter 3. I'm going to map it out in a way that relates everything so that you can see how Chapter 3 ties together. Chapter 3 is about linear functions, and I want you to take notes as we do this. So I want you to have something in your hands at the end of today that you could use on your test today. So Chapter 3 is linear functions. And what we're going to do to map it out like a tree map is we are going to have Chapter 3 is kind of the base of the tree, and we will have 4 branches coming out of it. So we're going to have function notation. Representations of a line. Arithmetic sequences. And linear regression. Alright, so function notation. There were 3 different ways that we could have function given to us. One way we could have a function given to us would be as an equation. And what a function looks like when it's an equation is it looks like something like f of x equals 2x plus 3. And when your function is given to you this way, your input is x. So your input is kind of inside the parentheses here. And your output is your answer when you plug x into your equation. So that's the output for your function. For example, if I wanted to know f of 3, that means my input is 3, and my output would be 2 times 3 plus 3, and then I'm going to pay attention to order of operations, so I'll multiply first. 6 plus 3, so my output would be 9. So that's an equation that's a linear, it's a function. I could also have my function given to me as a graph. And when my function is a graph, my input is going to be the x-coordinate of my graph. And my output would be whatever the y-coordinate is for that x-coordinate. So my output would be the y-coordinate of the graph. So the inputs are the x-coordinates and the outputs are the y-coordinates. But I could also have my function given to me as a table. In a table, my input would be the x values of my table, and my output would be the y values of my table. Kind of related to a table, I could also have a function given to me as a mapping. And in a mapping, the ones with the arrows coming from them are the inputs, and the ones with the arrows pointing to them are the outputs. So the 3 would be the input, 8 would be the output. 4 would be the input, 8 would be the output. 6 would be the input, 2 would be the output. All right. With function notation, we also talked about domain and range. And domain is going to be all of the x-coordinates and in order to make sure you're putting your domain in the correct order, you go from smallest to biggest, so you go from left to right. And then a range for a function is going to be a list of all the y-coordinates or outputs. And in order to put your range values in order, you go from bottom to top. In an equation, your domain would be the input values that you're putting into your function. In a graph, your domain would be the x-coordinates, also in a table. In a mapping, the domain would be the inputs, and the range would be the outputs. All right. After we went over what a function was, then we started looking at the particular brand of linear functions, and we said, well, I can represent a line as an equation. And if I have a linear function, then there are two different kinds of equations that we really spent some time on this chapter. One kind of equation would be the slope-intercept form of the equation, which was mx plus b. And in that form of the equation, m is the slope, which would be rise over run, and b is the y-intercept. And that's called the slope-intercept form of an equation. But we could also give you an equation in the other form that we talked about this chapter, which was the point-slope form. And in the point-slope form, you don't need to know the y-intercept. You can figure it out if you have any point on the line. So in this form, m is the slope, which is rise over run, and x1, comma y1 is any point on the line. And we talked about how you can take this form of the line and turn it into a slope-intercept form if you distribute the m and then add like terms to simplify. We also talked about representing a linear function in a graph. And so if you have a graph of a linear function, you would have a y-intercept, which would be where that crosses the y-axis, so that would be b. And then you would be able to count a rise over run to get your slope. And you get your slope by counting how far up each point goes and how far over, and that gives you the rise over run. Uphill lines would have a positive slope, and downhill lines would have a negative slope. And then we also talked about how you can have a linear function given to you in a table. And if your linear function is given to you in a table, then you know you have a linear function if you see that your table has a constant rate of change. So maybe you start at -2, and maybe your y-coordinates start at 3, and you can tell that this table has a run of 2, because the x-coordinates are counting by 2, and it has a rise of 5 because the y-coordinates are counting by 5. So you can tell from the table that you have a slope that is the rise over run, or 5 halves for this table. You can also find the y-intercept in the table, which would be when x is equal to 0. So for this table, it's b equals 8. It's when x equals 0. It's the y-coordinate when x is equal to 0. Right, then you talked about arithmetic sequences, and there were two different ways that you learned about arithmetic sequences. The first one is the recursive formula, and for a recursive formula you always need two things. You need a starting point and you need a rule. So your starting point is a with a little 1 next to it. That means your first term. And then if it's arithmetic, the rule is always either going to be that you're adding an amount or you are subtracting amount. So it would be you take your previous term and you add something, either positive or negative. If you have a recursive formula, the only parts you ever change would be these two numbers. That's the only part you ever change. For example, if your if your sequence is 2, 7, 12, 17, etc., then you would say, well, I know that my first value would be 2, and that my rule is that I'm adding 5. So that's our common difference. You also learned the explicit formula, and the benefit of the explicit formula is you don't have to find all of the previous terms in order to get the next one. You can just say, I want to find the 100th term. And so the way you do an explicit formula is I would take my nth term would be my starting amount plus a whole bunch of common differences that I added on. The only one I didn't add a common difference on would be the first term, so it's going to be n minus 1. For the example that I had, and again, the only parts that you ever change would be the d and the a sub 1. Those are the only parts you ever change. So if I wanted to write the explicit formula for this sequence up here, I would say, well, that would be a sub 1 is equal to 2 plus 5 times n minus 1. I'm going to make that 5 yellow too, so it stands out more. And then sometimes your teacher wants that simplified, so if you're going to simplify that, you would say, well, that would be, I distribute the 5, so I'd have 5n minus 5, and then I have some like terms, so the explicit form would become a sub n equals equals negative 3 plus 5n. All right. And then finally, you did linear regression. And linear regression is going to pop up on your calculator screen for you as y equals ax plus b, and then you'll have an a number, and you'll have a b number, and you'll have an r squared number, which you're going to ignore, and you'll have an r number, which is your correlation coefficient. A is the slope, which is the amount that your value is changing. It's the rate of change. And then B is the initial amount, or the y-intercept, but if in a word problem, it would be the initial amount, or starting amount. And then R, because you're going to ignore R squared, R is the correlation coefficient, and the correlation coefficient tells you how good your estimate is. If you have one that is close to 1 or close to negative 1, then you have strong relationship between your numbers. And if you have one that is close to 0, then you have weak relationship between your numbers. And then, so correlation coefficient tells you strength,